benzene. Benzene has a molecular formula C6H6. The structure of benzene was determined by Kekulé. The structure consists of 6 carbon atoms in a hexagonal ring with alternating single and double carbon-carbon bonds. Here is a skeletal display, and this is the structural display. This one is double bond, single bond, double bond, single bond, double bond. And you got a carbon here, carbon, 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 carbon. We're not showing the carbon hydrogen because they are hydrocarbons. So you don't have to show hydrocarbons, but you have to show any other elements. So in this case, if we show the carbon, so that will be the carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. The structure of benzene consists of a single bond. So that's a single bond, single bond, single bond, single bond, single bond, and a double bond. The single bond is a sigma bond. So that's called sigma bond. And the double bond is a combination of sigma bond and pi bond. And the pi bond is this one here, the p orbital here. So that's a p orbital forming a pi bond. And so we can say this one here is a p orbital. As you know, orbital is the probability of finding an electron. So that's a p orbital. And the p orbital kind of overlap. So if I bring that up here, and the p orbital is here, you see, and so that's carbon with the p orbital, carbon with the p orbital, carbon with the p orbital, carbon with the p orbital. And now this p orbital, the top ones, the orange, yellow ones overlap to form a ring, and the bottom one also overlap to form a ring. So now we have 2 rings, one on top and one below. What we now need to do is take the bottom ring, put it there, that's the bottom ring there, and the top ring, take that one and put it there, that's the top ring. So now you've got this ring on top and ring below, and in between is the hexagonal shape of the benzene. So now we can draw the carbon forming another carbon. It's carbon, 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 and carbon. This carbon will form with a p orbital on top and below. So that's a p orbital on top, that's p orbital below, p orbital on top, p orbital on top. So now in drawing the p orbitals, you can see that the top orbital will overlap, so the yellow ones will overlap, forming a ring, and the bottom orbital will overlap to form their own ring. And you now have the sigma bond of hydrogen there, and sigma bond of hydrogen, sigma bond of hydrogen, sigma bond of hydrogen, and sigma bond of hydrogen, sigma bond of hydrogen. So that's benzene structure. So in this structure here, I would have hydrogen sticking out like that. Hydrogen, 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 and perhaps hydrogen there. But in the middle is where the carbon will be. And this carbon has something called sp2 hybridization. So that's an sp2 hybridization, and the sp2 hybridization are what we call a planar structure. So that's planar. If you have sp2, it's more like a trigonal planar, and the bond angle here will be 120 degrees, 120 degrees, 120 degrees. So we're looking at the bond angle there, there, and there. So those are the bond angles there. So it's planar. The blue are the electrons at the bottom here. Those ones, when they overlap, or these electrons here, the bottom one and the top ones are what we call delocalized electrons. Delocalized electrons, because those electrons are able to move around the surface. So the yellow ones, electrons, will be moving along the surface there, and the blue electrons will be moving along the surface in the denominator there. And so those electrons are delocalized. Delocalized means they are free to move. So basically they are free moving electrons. So you can see that each carbon atom here, that's a carbon atom, form 3 sigma bond. So that's a sigma bond here, sigma bond, sigma bond. So that's a sigma bond here to hydrogen, sigma bond to carbon, and sigma bond to another carbon. That's where they form the planar structure. So that's where this is coming. Carbon, carbon, sigma bond, carbon, carbon, sigma bond, carbon, hydrogen, sigma bond. And that's where that's coming from. And they tend to form something called the conjugate pi system. So this ring, the top ring and the bottom ring, then end up creating a conjugate pi system, which we're going to show next. So this is the conjugate pi system. Conjugate indicating that you got single, double, single, double, single, double. That's what you call conjugate. So this is conjugate or conjugated pi system. Why pi? Because the pi here, this one is a sigma bond and the top one is a pi bond. So I could use an arrow diagram to just describe that. That one here is sigma bond and sigma, which has a symbol like that. So that's a sigma bond. And the top bit here will be a pi bond, which is pi for pi. So that's what we've got. We've got pi bond, sigma bond, pi bond, sigma bond, sigma bond, pi bond, sigma bond, sigma bond. So when you have a system like that, which is a double bond, single bond, double bond, single bond, double bond, single bond, we call that conjugated pi system. And these conjugated pi system, they're not fixed in this shape, and they are constantly flipping between the two of these, so that here we'll have a pi bond, and this one will have a sigma bond, that we have a pi bond, that we have a sigma bond, that we have a pi bond, which is what you're seeing there. So this structure actually is dynamic. It's constantly transforming between these two structures, and therefore we represent it as a single modern structure today as a circle in the middle to represent the continued dynamic exchange of this shape here. So that's why we've got this shape here, and this is now the structure we use for benzene today. And you can see the conjugate pi electron system there. That's a ring of electron, and this ring is showing delocalization or delocalized electrons in the ring.